everyone. Thanks for the introduction. I'm Tomasz Trzciński, a difficult last name, and I want to tell you a little bit more about Siamese twins and how to learn distances using end-to-end deep neural network architectures. So since we're talking about Siamese, I guess some of you actually have this memory of Siamese being connected with Siamese cats. This is a Siamese cat over here. It's going to join our lecture today, and there is a small quiz at the end. If you can count the number of Siamese cats that will appear overall through the lecture slides, at the end there will be the solution of this and maybe some surprise at the end. All right, so my short bio, I'm an assistant professor at the Warsaw University of Technology. I was also a visiting scholar at Stanford this summer. My background is actually in computer vision and machine learning. I started in 2010 when neural networks were just about to blossom, and the community of computer vision, and now, as you know, computer vision is mainly driven by machine learning and deep learning revolution. I did a few internships at Google, Qualcomm, and Telefonica over my career, and now I'm also a chief scientist at Triplet, a software service company where I lead a pretty amazing team of 15 machine learning engineers and data scientists. So today I want to tell you a little bit more about Siamese neural network architectures, and as a reason why this lecture should be interesting for you as this intro of iPhone X.
This is a phone we've been dreaming about for a long time.
Which will not be heard all over the place, but I don't know if you've seen this one. It's basically the head of engineering or VP of engineering Apple presenting a new iPhone X. He tries to unlock it with Face ID, which sort of doesn't work. Yeah, they try to explain this problem by saying that somebody was using this phone before he got on stage, and because of that, he couldn't unlock it. But the question that we want to try to ask over today's lecture is, would that happen if Apple uses Siamese network to train their Face ID recovery tool? And my hypothesis is that it would. One of the reasons is that FaceNet, which is a pretty amazing facial, descriptor, you can call it, or embedding, trained using Siamese architecture, reached 99.63% on labeled faces in the wild data set, which is one of the most commonly used benchmarks in this field, with state-of-the-art being at 99.83. We'll talk a little bit about this particular application, but in general, what Siamese allows you to do, actually, this architecture and this setup, is to learn distances between faces and then threshold based on those distances. And that's why it gets pretty high on many recognition, retrieval, matching, distance learning tasks. Other applications that you might find quite useful, this sort of architecture, are recommendations. So when you search for something that is similar in one space or the other, you typically use some sort of a distance. Either it's similarity metric, or it's closeness or proximity in terms of style or in terms of colors or so on. This is a solution that is, I'm not entirely sure if it's using, I think it's using also Siamese architecture, but in general it also shows you the scope and the spectrum of applications that you can use this architecture for. And then the last application, which will serve as our case study in a sense, is visual search. When you take a picture of something that is interesting from your point of view, either it's a clock or a skirt or a dress, and you want to search for something that is similar, there are several apps, several companies that are heavily investing in this because the e-commerce market is growing so rapidly. Here as well, you need to find some sort of similarity, some sort of a distance of the objects that you have in your database to the object that you're looking with. So to summarize the distance similarity metric approaches, one of them is Siamese neural network architecture, and also the extensions of this are fairly useful for four main tasks that are very often appearing in machine learning and computer vision, NLP, and so on. Matching, when you want to match one object with other objects from a big data set. Retrieval, when you want to retrieve something from a big data set, like, for example, the similar objects or similar shoes or similar skirts and so on. Recognition, when you want to recognize somebody or something, like with the face recognition task. And re-identification, so when you want to identify somebody. That's pretty much it when it comes to the reasons why we're interested in this sort of solutions. So let's jump into the first case study or first problem that we can solve with distance learning approaches. It's classical visual search, so visual search, and this is the classical approach, and then we will move on to the end-to-end learning of this problem. So visual search in general, as you saw in the previous slide, it's the task of using one object, or actually a photo of an object, to retrieve a bunch of items from your data set. Since it's visual, it's focused mostly on images. So you use typically one image or several images of an object, and then you go through the database and you retrieve the most similar ones. How it was done in a classical computer vision, or like it sounds like as if it was 500 years ago, but we actually had this sort of solution, and it's still implemented within imagesgoogle.com a couple of years back. But before deep learning approach was using, first of all, key points. These were the parts of the image that were identified as those repeatable across different viewpoints, across different objects, or across different views of the same object. Stable, so there was no flickering when you had a video of an object and then it was taken frame by frame. There was no flickering when you were using those kind of stable key points, or that was the goal of the key point detection mechanism. And they were distinctive, meaning that they were not concentrated around one point of the image, but they were sort of covering more or bigger parts of the image, and then they were different from the other. Methods that were used for key point detection, or are still actually in use, are corner blob region detectors, such as Harris detector, difference of Gaussians, or the fastest and the most simple one called FAST. Once you had your key points detected, you will then need to describe them somehow. So this is the second part of your matching procedure or your retrieval procedure. You want to describe your key points with some form of a vector. Either it's floating point or binary. It has to be discriminative, so you cannot have two descriptors of different visual patches be described with the same way. And there should be invariance, so that whether there's a different affine transformation, different viewpoint, different angle, different illumination of the scene, you should have the same descriptor of a key point. So it should be more or less similar. Methods to do that were numerous. People are still actually inventing new descriptors in a sense. This is a fairly big area of research in computer vision. These were either SIFT, SURF, DAISY. These were the floating point descriptors. I'll talk a little bit about SIFT more in the next slides. Brief, orb, freak. These were binary descriptors, so those that are super fast to be computed and also very short in terms of memory. And also the machine learning inspired descriptors such as LDA hash or BinBoost. SIFT. So this is one of the descriptors that has gained fairly big popularity. It's still very often used as a baseline, which is quite impressive given the fact that it was introduced in 2004, so 15 years, almost 15 years ago. The idea behind SIFT is to divide patch around the key point into cells, so into smaller patches. This is, as you see in the picture, you first see the blue and I think it's red as well. The key points that are being detected mostly at the edges. This is where the difference of Gaussian typically fires. Then around the patch and around the key point, there was a patch extracted where we computed the gradients. Gradients, so the directions of the edges that you see in this neighboring patch. Later, you would compute a histogram of those, so you would kind of make a fixed size vector out of those gradients and normalize it with respect to the dominant orientation, and so that they actually, L2 norm is 1. Once you have those SIFT, you will have a 128-dimensional descriptor of floating points. That's quite a lot, and it basically means that you cannot store your descriptors any other way than just by storing those millions of 128-dimensional SIFTs. So what people thought about is trying to use this concept of visual words. Like words are in a case, in some sense they are, or they can be represented as one-hot encoding, which you might have heard of. These are like basically mappings between the word in the dictionary and a full vector of zeros and only one at the place where the word is, where the dictionary represents the word. Here we have, or people thought about similar idea. Now the problem is that there is no such a thing as visual word. I mean, basically there is a saying that image can tell you more than 1,000 words, and this is actually the case. Images are very, very different from each other. So what people tried to do is they tried to use K-means, which is a unsupervised clustering mechanism, to find some sort of patterns within those visual words. And once they have those patterns, they identified a number of patterns using K-means, and then they store the quantization cell to which a given SIFT descriptor falls instead of the whole 128-dimensional vector. So from 128, you end up with just one number typically. Those key points are semantically similar. So you see here that these are several of the visual words, or the patches that correspond to the same visual words, and you see that they are fairly similar. Okay, so we're good. We have visual words. Now, how do we go about representing the image? Once again, we use histogram, and here we use actually histogram of visual words, and that is called a bag of visual words and very common in the literature. So given the images that you have at the top, you take them apart, you detect key points, you describe each key point with a SIFT descriptor, which is then quantized, and you have a histogram of those quantized visual words. Now, when you have one image, you basically, so the representation of a given image is just a histogram of visual words, which is great, which you can basically modify. You can modify the size of this representation. You can compare the images using cosine similarity between different images. This is pretty amazing and really fast to be applied. To speed up the search even more, you have a structure called inverted file, which basically is a bunch of visual words and the images corresponding to those visual words. So when a new image comes in, you look at the visual words, you nominate or you find the candidate images from your database that already had the same visual word previously identified, and then you just look at the union of all the candidate solutions, and you go with a cosine similarity, for example, between the bag of visual words as a similarity search. And finally, once you find these similar images, you should probably look at the geometrical verification of those images. As you saw in the previous slide, the histogram basically gets rid of the whole geometrical information. So you don't know exactly at which point of the image the visual words or the key points were identified. You just work with the aggregation of descriptors. Therefore, you need at the end some form of validation that it actually makes sense, the matching that you just performed. So this is the overview. As you see, it's pretty complicated. It starts with a query. You have a key point extraction. You have visual words. You have a bag of visual words, inverted index, which retrieves you a bunch of candidates, and then through the post-processing, you retrieve the closest cat to what the query was. It's not really intuitive in a sense that it doesn't really show you what sort of objective you're trying to maximize, what actually is your goal. Like what you can do is you can try to tune each of those elements, but you don't really have any option of tuning the whole system. So the question is it worth the hassle? So is it really necessary to go through so many different steps? And I know it took a little bit, but I wanted to show you that this is pre-deep learning approach, which was very common for many other applications as well. So if you see any system that consists of several modules like that, you might intuitively think that there is a way of simplifying this. So let's look at this from a bigger perspective. This is basically a representation. So whatever you do inside this orange block, at the end of the day, what you get is some sort of a representation of an image. Either it's a vector or a scalar, but it's a form it's a representation of an image that is coming into your system. And here you have matching. So you need to generate the representation and you match it somehow with the rest of your database descriptors. That's the whole point of this infrastructure. So the question is, can we simplify this, and can we improve it looking into the submodules? We can think about better representation. We can learn the representation not using those several elements of the pipeline, but use the Mahalanobis and other learning mechanisms to make sure that the representations of the similar images are close to each other. So I don't know how many of you have seen the Mahalanobis distance, but in principle, it's the unsupervised machine learning algorithm method to make sure that the descriptors that are, so that the distances that are in Euclidean space actually make sense for your distribution of the data. When you see in this image the points that are clearly displaced within the elliptical circles, using Euclidean distance between them might not make as much sense as using other form of weighted distance, such as Mahalanobis distance, which takes into account the covariance matrix of the input points. Other ways of learning representation, such as Fisher LDA, can also use additional information, such as labels. So when you have labels of data that are coming from 1, 2, 3 clusters, such as in this case, you can try to learn another representation that maximizes the distance between the clusters while minimizing the distance within the clusters. And so then when you project your data on other subspaces, you get a better representation, one that is more discriminative in general. And then you can start using the deep neural networks that were trained for other purposes, such as those pre-trained on ImageNet, and fine-tune them for a specific object that you try to retrieve, such as clothes or furnitures. So this is actually the case for most of the applications that, or the simplest case for the application when you already want to use something from deep learning. You just take the classifier that was trained for classifying ImageNet objects, and you tune the last, or well, you can tune the whole thing, but typically people would start with the last layer and then just try to make sure that it actually corresponds to the data that you have in your data set and tries to learn representation over that. You might also want to think about patterns like textures within your objects. This is a pattern net which basically fires on the same textures, in this case the buses, and you can concatenate those representations as a form of representing your image. But overall, you end up with still 2 submodules, which is representation and matching. So now let's look at better matching. We can use, instead of the spatial verification tool or spatial verification algorithm for query, for matches verification, you can use half transform, which is a fairly useful method when you want to, for example, represent objects such as circles or rectangles in 2-dimensional space instead of the Euclidean space, or more sophisticated quantization methods. Product quantization is one of those methods where you basically split your input vector into subvectors and you quantize them separately. as you see, these are fairly complex and complicated things. So the questions that still remains is, can we learn everything jointly? And that's where the end-to-end learning kicks in. And that's why we are so happy about deep learning and what sort of opportunities it actually brings. Because now you can link directly the input of your algorithm with the objective function that you want to maximize. And what you actually want to do in this case is just to make sure that the items that are close to or that are similar are close to each other in some space, while those that are far away or you don't want them to be retrieved, they're super, super pushed away from each other. And that's where the similarity learning is actually fairly useful. So what are the methods that we can use for learning this similarity? So learning this distance in the space of your representation. One method is regression. So you can think about it as a typical regression problem when you want to estimate some sort of an output of a function. Now the function is actually the similarity function. What is the problem that you can think of in this case? I guess I'll tell about it more in the next slide. But in principle, the function you will need to learn, or you will need to know it in advance. So you'll need to know that the distance between these shoes and other shoes is 0.1. Now between somebody else's shoes and somebody else's dress is 0.5. Why so? Why not 0.7 or 0.9? It's hard to say. So it's kind of complex, or it's kind of complicated to make up this proper similarity distance function that you want to train, and that's why it's not so useful. Other approach is classification. So this is what Siamese network will be useful for. So you want to classify pairs of images or pairs of samples that are coming in as either similar or dissimilar. You basically map the problem of similarity learning to a simpler problem of classification. Are these two shoes similar or not? Fair enough. And the third, where triplet networks are quite useful, and triplet networks are a simple extension of Siamese architecture that you might also find very useful in your experiments, is when you want to have a ranking. So something is closer or something is more similar versus the other thing that is less similar. So let's say that these shoes are more similar to mine, but these are totally off. If you have those sort of relations, and if you want to establish those sort of relations through the learning, triplet network is your friend. So to give you intuition behind this triplet learning, this is Dilbert's comics where the girl says that I used to compare all men to my ex-boyfriend. Now I compare all men to the entertainment standard of my smartphone. And Dilbert says that he only scored a 2 on the smartphone scale, but I was a solid 5 compared to someone named Larry. So you see, it's much easier in general to find those kind of ranking-based distances when defining an exact 2 to 5 measure might be a bit difficult, and that's why regression is not really that often used for these problems. But nevertheless, let's go through the regression problem. So the goal in this case is to regress the similarity. So you basically have some sort of data set with objects, and you know exactly what are the distances between your objects and your data set. Then you have a function that takes those objects into account, pairs of them, and you want to regress this distance that you have between those two objects. The loss function that you can use is based on the pairs, and you can add some regularizer on the weights. But in practice, as I mentioned, it's fairly difficult to train. You need a very, very specific knowledge and very precise information about the distances within your data set that very often you don't have it. And you don't want to go through the pain of actually labeling everything by yourself. So what is easier to be implemented is this classification task where you have a pair of points, for example, pair of images like those at the top of the screen, and then you want to classify them as same or different. So you have a 2-channel network where you basically input concatenation, or like 2 separate images at the beginning, and then at the end you have a classification module which tells you if those 2 images are same or different, so 1 or 0 or 1 or -1. as you want. Now, is the cross entropy, which is the most commonly used entropy loss or objective loss, useful in this case? So cross entropy will not give you any notion of the distance. It will just tell you if those two classes are correct, or if the label is correct or not correct given the prediction. What you actually want to make sure of is that you also are aware of modifying the distance in this space that you're trying to model. So let's say that, and that actually comes more into the next slides, let's say that the distance between the similar items, you don't want to have it bigger than 0.2, and those between the different ones, you want to have it larger than 0.5. This is your assumption, because that's how your classifier will make it easy, or your application is going to be more easier to make this split. Now, in this case, when you use the cross entropy loss, you don't have any notion of margin, any notion of distance at all. So that's not really very useful. Now, what is the solution that is proposed in the literature? Is called the contrastive loss. And this is where you are able to not only find or penalize those incorrect pairs that were labeled as the same, or those that were labeled as the same while they being different. You are also able to actually introduce a margin, which is in this equation a letter m. So let's go through it very quickly. As you see, there is a fairly similar formulation as to logistic regression. You have 1 minus y and y at the end. These are the two labels that define whether the pair of images is similar or not. And you have d, which is the distance between those. And this d can be defined in many different ways. One of the simplest ones is just the Euclidean norm in your space. Y, as I mentioned, are labels of your image patches or data points patches, and m is margin. So in this case, you have two images of ducks. At the end of the submodules that you're training, you get f of x and g of x. These are the outputs of your convolutional or other neural network. And what you want to do is you want to compute the distance between them. That's where the d kicks in, and that's where you see the distance being Euclidean distance. Y is the label. In this case, it's going to be 1. If you had a duck and something else, a stork, for example, you would get 0. And m is the margin that you want to push your negative samples or negative dissimilar samples as far as m, and that's why it's m minus d at this second phrase or second term of the equation. All right, other loss functions that you can use. You can also use, this is actually something that is called modified contrastive loss, where the square from the second term gets into the distance. The main difference between those two is how you penalize your negative samples. So the y equals to 1. This means that your image pair is actually the dissimilar one, and either you penalize them, and this is the loss function, so you want to minimize this, and therefore at the beginning when you have a distance equal to 0 between your pair of dissimilar matches, this is not good, because that means that two images that were supposed to be different, they have distance 0 to each other, which obviously doesn't make sense. When you use the square term at the end, you see that this loss is diminishing in a square manner. Now when you use the d square within the m, then this is slightly more penalizing those pairs that have actually distance very close to 0. This is slight modification, but it might help you a lot when you're training your classifier. You can also use distance-based logistic loss. So it basically is additional way of defining your distance through this e or exponential transformation. There is several other papers that discuss other types of loss that you can use over here. My point here being that this doesn't have to be contrastive loss when you're using it with your Siamese architecture. It can be any loss that comes to your mind, as long as it penalizes the discriminative or the dissimilar pairs as much as possible. All right, so you saw in the previous slide that these are actually two submodules, so two networks that have at the end okay, that should be G, that have a different output. So on the left, this is a blue submodule network that takes the X1 or X superscript 1, and this is the green one that takes the second image as an input. Now, what can happen is actually that you can use the same network on the left and on the right. This is where the sharing starts to occur, and that's why we call it the weight sharing, and this is exactly the definition, the very definition of a Siamese neural network. And that's why we call it this way, because you basically have exactly the same structure on the left and on the right. You have two identical networks on the left and on the right, which means that you can then substitute or you can permutate the order of the inputs, and you will still get the same output. The loss will not be affected by changing X1 and X2 and substituting each one for the other. So, Siamese networks, this is exactly the point or the main topic of this lecture. Siamese architectures, as I mentioned, are basically consist of two submodules of identical structure. What it means is that they have the same configuration, they have weight sharing that is occurring between those submodules, and also they have identical updates. So when you're training your Siamese architecture, you're getting exactly the same update on both of those submodules. We'll explain exactly how we actually how we compute this update, but in principle what you should remember is that the update is exactly the same. So both of those at every single moment of your training should have the same weights in your code. Now, why is it so important to have them exactly the same? First of all, as I mentioned, you can permutate your inputs, so it doesn't mean doesn't change if you input the image number 1 as the first one, image number 2 as the second one. You can then shuffle it, and that's going to work as well. Of course, for training, you might want to keep them as they are, but for the testing, and this is actually fairly important message when you want to use this architecture for similarity learning. When you have your images or other data points in your database, you will apply this submodule network architecture on all of your samples offline. So you will generate a bunch of vectors that represent your images in your distance space. When the query comes in, you will just be able to do matching or do retrieval through the fast k-nearest neighbors search. If you didn't have this character, or if your network didn't have this characteristic of being exactly identical, so having, for example, the input different than the other, that means that you would not be able to actually compute those weights offline, because you would never know if the input is coming from the node or from the subnetwork green or subnetwork blue. This way, you are able to reuse all the machinery that is there in the field when it comes to k-nearest neighbor matching. And this is fairly powerful. You can use approximate nearest neighbor methods, you can use KD trees, you can use HK means to cluster that. You have tons and tons of methods that can be implemented here. Now, what might be a little bit off, or might be a little bit different from what I just said, is those sub-Siamese networks, or those that are actually partially sharing, partially not sharing the weights. This is the slide that shows that there are many ways, many methods of using this concept of weight sharing across different Siamese and non-Siamese architectures. So one architecture fits all, that's not the case in here. If you want to, for example, have some multimodal learning or some transfer learning through different modalities, you can actually modify the Siamese sub-networks in a not so obvious way. You can actually have parts of the network that have shared weights, like those that are in purple over here, and those that have unshared weights, meaning that they are separately trained for left and right. What is the problem, or you have to remember about when you're using those kind of architectures, is that you need to always make sure that the order of the inputs is the same as when you had the one that you had during training. So say that patch 1 in your case is sketch, and patch 2 is image, and you're doing sketch-based image retrieval. You will always need to feed your sketch into the network number 1. Otherwise, it's going to get too messy. So for training, as I mentioned, I wanted to tell you a bit more about the updating the weights in your Siamese architecture. You should update each of those independently when it comes to just propagating and getting back the error. So the error computation on your subnetworks will be different, but then the average of those weights update will be propagated through the network for the next iteration. So the propagation is done independently, but the updates of the weights coming from the patch number 1 and patch number 2 are averaged and then propagated, and then the network is updated according to those the averages. So that's it from the training part. Let's move on to, yeah, so probably some of you have seen this before, but if you haven't, then just take a minute to go through it. Personally, I like the Jan LeCun one the most, obviously, because we all think that we're like him. What it actually ends up being at the end of the day is import Keras. So I want to give you a short 2-slide example of how you can actually use Keras to implement the Siamese neural network architecture. So everybody had their laugh of this? Can we move on? Oh, yesterday you had a even better. So now you're going to remember it even better. It's a very useful one. So how does it work in Keras then? You have import Keras, and then you have your input. Your left and right input in this case are equal. These are of 105 by 105 with 1 depth dimension. And you build your convnets. This is actually an example that works with images. So, well, it doesn't have to, but in this case, I think it was images. These were images. You create your convnet submodule, subnetwork on the left, and subnetwork on the right. You add some convolutional layers, ReLU, with kernel initialization, and then you add max pooling on top. This is a very simple network, just with one convnet and one convolutional layer and max pooling, but it just serves the purpose of showing you where you actually add the Siamese element to your code. And here you create 2 legs of your network, encoded L and encoded R. These are actually these are going to represent your embedding spaces. So when you take your left image and you apply the convnet on your left image, you will get the encoding. You will get some sort of a representation of your image in the space where ideally after training, those that are similar should be very close to each other, while those dissimilar will be far away. Now you define the distance. In this case, it's L1 just for simplicity, but it can be any other distance. You define it through lambda. You can have as much fun as you want over here. You can weight it, you can do Euclidean, you can do infinity, whatever. It's all good. And that's the key element of this code is to merge L and R, so both of the subnetworks in one place using L1 distance, and this output using the lambda. So now at this point you have your network that merges 2 subnetworks into one. When you have the prediction, you use, that's also up to you, but in this case we use a sigmoid. And Siamese net as a whole is the model that you just created. And then you can optimize it using Adam or other optimizers, and you compile it with contrastive loss. So for Keras, you need to write your own contrastive loss. By default, you can use cross entropy. This is fine for this purpose. As I mentioned before, there is one big problem with cross entropy, which is the fact that you cannot define your margin. But if you can live with it, then it's not a big deal. All right, Triplet. So let's say that you already have your Siamese network figured out. You know what pairs of images or what pairs of data points are similar, which are not similar. Now you want to empower some, or you want to extend it to some more natural ranking-based systems. And for rankings, the simplest way of ranking is triplet. So you have something that is closer to the anchor, which is the base object that you define, and something that is further away. So say that it's closer from here to Poznan, but it's further away than London. This is a fairly natural way of reasoning, and it's much more effective when it comes to training too. The architecture of the data points that you need to create for this purpose are the following. You have anchor, a vector or anchor data point, which serves as a point to which you will compute your distance, or to which you will you compare the other examples in your data triplet. And you have negative and positive sample. So negative sample is the one that you want to push as far away from the anchor, and the positive one is the one that you want to have as close as possible. So through learning, you basically apply whatever methodology you want, but at the end you want to have it as in this red rectangle. And the architecture that actually is fairly useful for this purpose, it's called triplet architecture. It's a three-branch network. It has, as before, the blue duck and then two other images. Now, what is very important is, in this case, the positive and negative branches always share weights. And here there's no excuse, in the sense that you don't really, you will have in the triplet, you will have the same type of data for your positive and negative example. Anchor can be different, but mixing positive and negative here, doing some partial weight sharing and so on, doesn't make sense at all. Because these are coming from the same type of data, the same modality, the same pool of samples that you want to use. Anchor branch can share weights, for example, for intra-domain learning. So when you have all the images, or all the data points are images, all data points are same images or same type of image or same type of audio or NLP vectors. While where you have cross-domain learning, so for example, this duck is a sketch, so it's a different domain than the images, you can start to share only partially the weights. But again, this doesn't work for the positive and negative branches. And again, you have here A, P, and N. These are the outputs of each of the sub-modules, A being anchor, P being positive, N being negative patch, and you have a loss that depends on all those three outputs. So this is the loss. As you see here, it's a hinge loss, again, similarly to the Siamese case. And you have M, which is the margin. I will show you in the next slide what exactly the margin means in this case, which is slightly different than what it meant in the Siamese neural network architecture. You have distance, square distance between the anchor and the positive pair, and the distance between the anchor and the negative pair. Since you're minimizing this, the distance for the positive pair is with plus. You want to have it as small as possible, and the distance for the negative one is with minus. For distances, you can use Euclidean, you can use dot product. Again, this is up to you and depends very much on the space that you're working in and what you're starting with as your similarity metric. So what is the difference between the Siamese and triplet when it comes to this margin point, or margin concept of margin? So over there you have the before learning set of, or the relation between the anchor positive and negative data points before learning. And here you have the goal or the visualization of the margin for Siamese neural network architecture. So you have anchor and you have this parameter of n. You want to, through the training, to push your n sample as far away from the m, and you want to take the p as close as possible. So the m allows you to basically modify this parameter that the n negative sample will be pushed away from, and this is what you have penalized in your loss function. Now for triplet loss, the m is actually defines this semi-sphere, is it, or is a distance between the negative sample and the positive one. So this is before training, so you don't really see it yet, but if you actually follow up with the training, the P should get somewhere close to this point, to the inner circle of your visualization, and the N should be pushed away from it. And the distance between this negative and positive pairs should be at least as big as M. And this is exactly what you see in this triplet loss function. So this is a slightly different concept, but as you'll see in the next slide, is much more powerful. Okay, so architectures overall, to compare every single one that we mentioned so far. Let's start with the classification CNN. You have an input of two pairs, or two images, pair of data points. You feed it into the network, for example, AlexNet in this case, and you get the log loss softmax. That's up to you, but in general, this can be a fairly powerful architecture. These are the example of architectures used in the paper for aerial image retrieval, and this is a specific architecture that they use in this paper. The point of this paper is to retrieve images, and you'll see the comparison in terms of numbers, so that you more or less have a feeling of what's better, what's worse when it comes to accuracy. The second type of networks that you can think of when it comes to the pairs of images is Siamese. So you have two images that are coming through two submodules, subnetworks, and getting to the loss module, which defines, or which allows you to compute the contrastive loss, as mentioned in the previous slides. And then you have this M parameter that I mentioned as a margin of your loss, which can play a very significant role. Then you have a Siamese classification hybrid network. Ooh, we haven't talked about that, but what you can think of in general is just like a convnet, like a Siamese, but with a fully connected layer inside. So on top of that, on top of your two sub-modules that you have, you add one fully connected layer. This is not exactly the way that you want to code it up when it comes to image matching or retrieval in general, because you introduce, in this case, through this fully convolutional module, you basically kill all the k nearest neighbor methods that you could use in the Siamese network, because like the only way that you compute the similarity in this case is through this fully connected module. But in some cases, it actually works. And if you can allow that, if you always know that when you're going to compute your distance, you will be able to run your super fast 10,000 GPUs server cluster, and you don't care about speed, that's fine. That's okay. Like this is what they tried, and then it actually can perform pretty well. So let's leave it with that. And finally, you have your triplet network. So the one that takes into account and takes in 3 inputs, each one of them coming from either uncore positive or negative pair. It has 3 subnetworks that are propagating those images through to the loss module, and then in the loss, you have your triplet loss computed. So for aerial image retrieval, which is the problem of having a query to be matched with the images from satellite view, and that's the ECCV 2016 paper that those 3 architectures were taken from. You have the matching accuracy for 3 different US cities clearly improved by triplet net. And this is not only for this case. In general, triplets help you when it comes to increasing the accuracy of your retrieval. But what is interesting is when you add those classification networks and hybrid networks, you can boost it up even more. Now, as I mentioned before, this is cool. This is pretty interesting to have those sort of architectures. But the problem is that you cannot scale the matching with all the methods that have already been invented when it comes to k-nearest neighbor matching. So you can only use those when you are sure that at your runtime you can compare your query with every single input from your database using fully connected layer. Very often that's not the case, but if you can, it can also give you some sort of improvement of your accuracy. Okay, so now the training tricks. How do we make this thing work? So as you mentioned, or as we mentioned before, the training, I mean, the whole idea of Siamese is not spectacular. It's not something that nobody could think of. It's fairly natural extension of just single lay or single module, some network convolutional neural net. But what is important is when you get into the training, there are several intricacies that actually make this a bit more tricky to be trained. One of the most important things that we will also cover is the fact that you now need to properly model your input pairs and similar and dissimilar pairs space. So that's not, as I mentioned before, with regression, it's not easy to very often define what is the distance between your input data points that you want to regress to. Similarly, here you need to be very careful when you're selecting which images should be similar, which should not be similar. They have to be difficult. They cannot be too easy because then the whole network collapses. But we'll go through it very quickly in a second. So first trick that everybody knows is data augmentation. You can use your input query and you can crop it, you can rotate it, you can mirror it, and you can scale it up and down so that you have more data, especially if you don't have too much data in your data set. With cats, it's actually okay because there's plenty of them on the internet, so you're good. But with any other medical data, for example, or some tricky geographical or satellite images, that might be useful. Next thing is regularization. So there are several methods of regularization that you probably have heard of. One is the parameter magnitude regularization. In this case, it's the L2 norm of the weights to be added to your loss. You want to minimize this. You want to make it smooth so that there are no abrupt changes in your weight parameters. And then there's dropout, which some of you actually might have heard of. It's basically random shutting down parts of the network. There is a bunch of other regularization methods. Basically, every single conference you have more regularization patterns or regularization methods that are useful. In this case, you pretty much randomly shut part of your network, and then you select those subparts that are shut down differently at every iteration, so that you don't lose those neurons. Like, as an anecdote, it seems to me that this has been invented as some sort of a bug that became a feature. It looks like somebody actually forgot to link a few neurons, and then it boosted up results, and then they left it this way. But clearly it works, so we're happy to use it. Partial sharing. So as I mentioned before, you can consider sharing the weights between those subnetworks. Here you have the full share between in your Siamese neural network architecture. This means that you can use all KNN nearest neighbor search methods. No share, this is useful when you have multimodal or different modalities of your data set. And partial share, some of them are shared, some of them are not shared. That might be problematic when it comes to K in the nearest neighbor search, but in some applications it's actually very useful to regularize your neural network by just not allowing it to have so many different weight parameters. And weight sharing is actually one other way of reducing number of your parameters, because you basically have twice the same sum module network. And my favorite trick is, maybe hard to say that's a trick, but it's a very important part of your training. It's hard to do the mining of your examples. For in this case, yeah, that can be done for Triplet and for Siamese as well. So what you would think of if you didn't know anything about this problem, you'd probably start with just randomly sampling your image pairs. You would take 2 images and you would see if they come from the same class or a different class, or if they are similar or not similar, and so on and so forth. And this is what random sampling does for you. Now, what the problem with this approach is that you can find by random those pairs that are super simple. They're like always fall so much, like always there's cat and bird. And there's no pair of similar or dissimilar patches that is actually like cat and tiger, which in some cases might be actually mistaken for the same class in ImageNet. So this is a problem. What you can do is you can do hard negative mining for those negative patches, and basically for this case, for hard negative mining, you would take your anchor or your base object, and you would look for the short or for the nearest negative class example. So in this case, it's a swan photo, but not swan photo coming from the furthest part of your data space, but from the closest one. That means that you'll make sure that your network pushes away those tricky examples as far as possible. Now, for hard positive mining, you would do sort of opposite thing in the positive space. So you would take your anchor, your input object, and you would take this image that is lying in the same class, but as far as possible from your input in the space that you would typically use. So here it's Euclidean. This way you would generate a fairly robust set of hard negatives. You can do it offline, but you can also do it online. So when you start training your triplet or your Siamese network, you can actually generate those samples online. You don't have to generate them and store them on your disk. You can start picking those samples and pairing them up and putting them in triplets while you're training your model. So what is fairly interesting in the paper that was published at ICRA this year, it's actually coming from the Google Tango AR Core project, which we're also involved with, so that's why I know this example, but probably people have tried that also in other examples, is when you have your initial triplet set that you train your first set or first part of your neural network with, you can then project the samples batch back to your space of the dimension, and you can start picking those that were misclassified or those that were the most difficult to be classified as the same or different. And this way you can regenerate more triplets that are harder because you already misclassified them in the previous runs. So doing this online makes sense. You can also do the dimensionality reduction, which are the conventional methods like PCA or redundant analysis. You can use the dimensionality reduction in CNN. So here you have actually a fully connected layer that is followed up with ConvNet, and then you can reduce your samples, your dimensionality in this case. That's more or less it from the training part. Now let's move to I think it's one of the last parts of this talk, applications. So where do we actually use those? I mentioned a couple of examples at the beginning as a motivation for this talk, but here let's look into the exact solutions that are based on Siamese and triplet architecture. So FaceNet, the first network approach that I mentioned was FaceNet. It uses deep architecture with L2 norm and then triplet loss at the end. It has basically this beautiful function that looks very similar to the triplet loss. There is a margin here that is alpha in this case. There is a distance between the negative and positive pairs, and these are the results. So as I mentioned at the beginning, they got 99.63% on the labeled faces in the wild data set with 9983 being the state of the art. These are false positives that they generated using their method. So as you see, these are false positives, so they are incorrectly matched as the same. The images coming from two different people are incorrectly matched as the same, except for the last sample at the top, this one with the gray and non-gray hair. They are very similar, I think. So this is the only part, or the only pair that I would probably also be mistaken at. The bottom part of the image is false negative, so that those that are actually corresponding to the same person, that faces are the same, or the faces are correspond to the same person, but they were incorrectly labeled as different. And as you see, for example, over here, the main reason for that is the change of the haircut, which is quite problematic for other classifiers as well. And here, the color of the hair. So it's quite interesting that in one case, this was actually incorrectly mapped as positive, and in the other as negative. Now, the other results that they present are actually related to the robustness of those methods against the quality of JPEG compression and the number of pixels. And as you see, the number of pixels within so the resolution of your images doesn't have to be that high to get fairly good results. So it was 14,000 that was also making sense. And last but not least, the training images size. You had once you have 26 million images, and this is actually Google that published this paper, so there's no problem with using 26 million of personal face images. Then the method sort of saturates, so there's no additional improvement coming from more of those samples. Another example that is very close to our work at Warsaw University of Technology is deep descriptor. I mentioned in the beginning of this talk there is a few descriptors that were developed throughout years. Some of them are handcrafted descriptors such as SIFT, SURF. Some of them are actually using some part of machine learning. And this is the first, as far as I remember, fully deep neural network-based descriptor. It used a very often used data set of image pairs and propagated it through CNN to get the contrastive loss. And as you see here, the improvement over the traditional or the classical method is pretty significant. So it goes up to twice the, I think it's accuracy in this case on this data set as SIFT, which, as I mentioned before, is a fairly powerful baseline still used in computer vision. So I promise you a few case studies. Like I will give one case study more about the work that we have at the university. This is a quite interesting story about like using sketches, which you might actually have seen online, to retrieve images. So let's say that you want to retrieve images of cats or dogs or bikes or whatever else with just sketching the overall contour of your image. And this is apparently this is an important problem, especially in Japan, where they have like watches and they try to sketch something on their watch, and then it's supposed to be changed into emoticon or some object that they want to draw in their messengers. Some of the cool, trendy hardware watches, you already have that in Japan, and they have a fairly big need for that. So the problem is the following. You have a sketch of like a few contours around, and you want to retrieve the images that are as close as possible to this given contour. And the question is, how do we do it? What's the problem with it? What are the challenges that you have? First of all, this sketching thing is very messy usually. So I don't know how about you, but I'm pretty bad at sketching things. So there are different types of sketches that supposed to be mapped to the same object. Various levels of abstraction. So all of those sketches are actually describing a house, which for me, I think I got like tops here. Like I would not be able to draw those. But all of them are supposed to work fine when you want to retrieve an image of a house. And then there is this accuracy of description. So some of the sketches actually have very exaggerated parts, which are not exaggerated in reality, like whiskers of a cat. You don't see them in the images, but people and kids specifically, they draw a very nice whiskers when they think about cat. There's anthropomorphism, so people tend to add like smileys and ears to like spiders and stuff. So that also can be a bit problematic, and also simplification. So when you're drawing like a caricature of a human being, you typically use just a few lines, and that doesn't really look the same as the person walking. So what were the approaches that have been tested so far and have been published in the literature? Conventional shallow framework basically regress to the edge maps. You have an input image and you do the edge extraction. You extract the features from your edges. Sort of like with visual words, you kind of classify which edges are what, and then you build your histograms out of those edges. And when the query comes, you have a histogram of edges, and you just do the cosine distance computation. So you do the similarity measurement as in the case of bag of visual words. Other approaches were using structured tensors, so second derivative of the intensity of your black and white pixels in the neighborhood of, well, basically across the whole image. And then you have a dictionary, and again, you end up with some form of histogram or some form of vector that represents an image sketch. This is a method proposed in 2010. It got like a mean average precision, which is a most commonly used metric for accuracy on retrieval of 7.98. And you will see how over time those methods improve and get better. Local feature descriptors, SIFT, histogram of gradients, these are the descriptors that you probably, or you've seen in the previous slides. They allowed us to improve this result by another 3% of your accuracy. This task is pretty difficult. If you see the accuracy, it's 10% of average precision. It's not really what we're aiming at, but it shows that there is a potential in this method. So you try to look at the improvement more than just the nominal numbers. Another approach was perceptual edge. So it was proposed in 2015. The idea here is to take the contours of an image that you take as an input and then try to group the contours together through a graph that connects those that are important with those that are not important. So you have some sort of a simplified version of a contour. And this simplification allows you to actually generalize better across different objects. And when you have those perceptual edges also computed for the objects in your database, then you can map them more easily, and this is more, this gets you better results, up to 8% when it comes to this particular data set. And then Siamese, this is 2016. They used the Siamese neural network architecture with contrastive loss, fully shared weights, sketch, edge map. So you basically have a sketch that is moved to the edges and then mapped to the dictionary. And you input that as an input of your Siamese neural network architecture. The improvement over the perceptual edges is not significant, but when you use triplet networks, and this is again confirming what we actually saw in the previous application, where you had over aerial images, the query over aerial images, triplets once again show that they're very useful. Now, what is important over here is that you have 3 sketches as an input of your system. So the cat sketch is actually something that comes in as a query. Now the other ones, positive and negatives, are also sketches. And this is important because the next method that we will introduce, and the one that actually performs currently, I think, state-of-the-art results on this data set, is based on the sketch photo direct. So instead of feeding to the network the additional 2 sketches, you feed the images that are supposed to be retrieved directly. And you do a bunch of different ConvNet, hybrid, SketchNet modules inside. As you see, this is where you're allowed to play a little bit more with your architectures and do not exactly mirror the networks, some networks of your triplet net, because you're actually working with some sort of a multimodal or transfer model approach where you input the sketches, but what you want to retrieve at the end are photos. And the results that they got for a given set of queries are actually pretty impressive. Like if you look at, okay, the sketches are also fairly good, so the quality of the sketch is definitely not mine, but I mean, the horse is quite nice, the bike is extremely nice, not to say about the bridges, which are quite impressive. But as you see, the results are quite good. Back below, you see that they start to be a bit problematic when it comes to like plants. I think that the guy wanted to have a palm, but it actually looks like a flower, so that might get confused. But overall, the results are quite nice. Okay, so the second case study that we are involved at Warsaw University of Technology, we have a group working with Google AR Core, which supports our research, and is the system for simultaneous localization and mapping. I don't know how many of you have tried that or used that or know what AR Core is. There's AR Kit as well in your Apple. In general, it's a fairly broad number of methods that allow you to play with augmented reality. You walk around, you know where you are, you build a 3D reconstruction of the space around you that allows you to localize your mobile phone up to the pose. So you know where the mobile phone is looking at through the reconstruction of a 3D scene around you. For Google AR Core, this is actually the railway station in Zurich, where people go through, taking a lot of video footage, and based on this input and based on the mapping between the input points and matching different images, they were able to create or reconstruct the path of every single one of those guys. And so you see here that the paths were actually overlaid with the real 3D reconstructed scene of the railway station. And this is one of the capabilities of the system that we have. Basically localizing yourself using simply, it's just your image, nothing else. The image is coming from your camera. That's the goal of the project. You can also see it in another video where I think it's Simon Linen from Google Zurich, who rides down the bike from one of the hills next to Zurich, and he is mapped exactly along on the trajectory that somebody else before rode through. So those points that you see in yellow, these are the key points that are detected in the images. Then they are mapped to the 3D map of key points, and from this relation, exact pose of your camera can be defined, which is pretty impressive that you get this kind of precision on that. So one of the key problems in those sort of applications is relocalization. Relocalization happens when your phone basically loses tracking. So one part of this system is based on the frame-to-frame tracking, because you're not like teleporting yourself somewhere else, you're just moving in a smooth sort of a manner. So you track your images on a frame-by-frame basis. But when you cover your phone camera for a second and you open it again, you have to relocalize yourself. You have to look for all the images that you already collected. These are called keyframes of your neighborhood, and you need to find the closest one. So this is exactly the case that you see in this spot. And what we're working on and what we submitted as a CVPR 2018 submission is actually a new descriptor that takes into account not only a local neighborhood of a key point, but also the constellation or the layout of the key points around this area. So from using our descriptor with respect to the state-of-the-art that they use, well, maybe not state-of-the-art, but the descriptor that they use, you see that there is a fairly big improvement when it comes to mismatched parts of the image that are being aligned. So Frigg is actually giving you a lot of false positives that are discovered only through the geometrical verification step, which I covered briefly in the previous slide. Here you can actually see that this number is reduced. And how do we do it? We actually use Siamese neural network architecture for this, and we learn the constellation. The constellation embedding. So we have two submodules that are sharing weight and the Euclidean distance between those two submodules. Within the submodules, we have both the binary descriptors of the key points, their relative orientation scale, and we feed that in, and this is a comparison with SIFT. Actually, as you see here, there's a bunch of mismatches between those images which are not happening for our descriptor. So just to give you a kind of overview of this again, you have this constellation embedding module, which takes the whole constellation of the key points along with their descriptors, orientations, scale, and so on. And into account, there's a weight sharing happening over there, and then you have Euclidean distance as our loss, as our distance to be used within contrastive loss. Okay, so that's where the Siamese network is used in practice. As embedding, we take basically several descriptors along with their orientations. There's scaling as well. You concatenate, you embed it in a sort of consecutive manner, and the results are actually pretty impressive when it comes to the improvement over the baseline that they use right now. So this is the absolute distance between keyframes. It shows how, so this is our data set where you look at the matching distance between keyframes, meaning that over here at 0.4 you have really distinct, the frames that are very, very far away from each other. And when you have the distance close to 0, that means that you have, basically you're taking a frame that is very close to the one that you want to match. So overall, just to see the dependence on the distance between those three frames, it's fairly, performs fairly stable across all of them. And also when it comes to rotation and translation estimation, we are able to outperform the other descriptors that were typically used in those kind of applications. Okay, so to conclude, this is our friend. How many of you have counted the cats? Very good. So the price is that you can send me an email with your address, and I might be able to send you out actually a few chocolates, but also I might be able to update you on the results of our CVPR submission. And what's not, I can also send you some, I'm going to talk about it in the next slide, but some details about the upcoming projects that are related both to Siamese and Triplet nets. So if you're interested in maybe doing some cool research with the area of machine learning, deep learning, and Siamese and not, just drop me an email. That's going to be an email at the end of the slides, and then you can get your chocolate cat. All right, Siamese cats and networks are great. I think everybody knows that already. Triplet nets are even better. So you notice from the accuracy results that adding this additional level of ranking, so not only looking at similar, but also the negative, positive pairs is actually quite beneficial when it comes to the accuracy of the results that you get. And they are very often applied, or typically they are applied in distance similarity learning. And the reason why it's so important is because a lot of applications that you think of in everyday life are actually very much relying on this distance or similarity, concept of similarity. And if they are not, you can map it to this concept fairly easily. So face recognition, local feature matching, sketch-based image retrieval, SLAM, a lot of applications actually have somewhere embedded within their architecture the matching or the distance learning part. Okay, acknowledgements. I need to thank all the people who are actually working on this Google AR Core Tango project with me at Warsaw University of Technology, and I also stole a bunch of slides, so thank you for making this presentation as it is. And NVIDIA actually donated us our one of the first GPUs, the Titan X, which is quite rare at the market right now, so we're very happy, and we need to thank, or we want to thank them as well. So now, thank you. If you're looking for an interesting machine, deep learning, computer vision project, feel free to contact me or drop me a line. I'm available for questions now. Thank you.